Welcome back to a new episode on my exercise series Introduction to Physics. Last time we've been focusing on the statics of rigid bodies. Now this time we are going more to the dynamics of rigid bodies. And in order to do this we have to look at the moment of inertia. And with this and without further talking, let's get on with it. A company produces metal shafts in the shape of solid cylinders that roll down an inclined plane of length 2 meters during production. A. What is the maximum tilt angle if the shafts should roll not faster than 2.6 meters per second? Then, to reduce material, hollow cylinders are introduced with an inner radius of 80% of the outer radius, made of the same material. B. What happens to the velocity with respect to the full metal shafts? So what can we take out of it? We have given first of all the length L of our inclined plane with 2 meters. Then we have given the velocity, let's call it VA, that is supposed to be not larger than 2.6 meters per second. And we are actually searching for the inclination angle, let's call it alpha max. In the second part, we have introduced hollow cylinders. So we know there is an inner radius R, which comes from the outer radius, and it's 80%. So it's 8 divided by 10 times R, the outer radius. And in this case, we are searching for the velocity, let's call it VB, in relation to the given velocity VA. How do we solve it? Well, as always, let's make a little sketch. And this is a very basic, very simple sketch. We see that during production there is an inclined plane of given length L, and our cylinder rolls down this plane. Then we know in such a case there is energy conservation. So on the left hand side, when the rolling starts, or before the rolling starts to be precise, we have a certain potential energy. And at the end, on the right hand side of our sketch, we assume that there is, say, a basic level reached, so the height equals 0, then we have only energy of motion. And in this particular case, yes, we have the energy of the translational motion, which we can call, say, E kin, like kinetic energy, plus in addition we have the energy of the rotation. And in order to solve this equation, we need the basic equations for all three terms. Potential energy is always the product of mass m, gravitational constant g, and height h. In contrast, the kinetic energy is m divided by 2 multiplied with the respective velocity, in our case VA squared. Plus, and this is actually new compared to our previous videos, we have the rotational energy, which is J divided by 2 times omega squared. Now, what are these two new variables J and omega? J is the moment of inertia, respectively the rotational inertia, with respect to the axis of rotation. And for a solid cylinder, this one is known. It's simply J equals m divided by 2 times radius r squared. In addition, omega is the so-called angular velocity of the rotational motion, and it's relatively simple. Omega equals v divided by r. Well, this being said, we can now use these two new equations to substitute the two new variables in our main equation. And what we get looks slightly blown out of proportion, but we can simplify it. On one hand, we can simplify the second term on the right hand side on the other side, we can divide our whole equation by mass m, which means, of course, that the mass is not important. And what we get is that g times h equals 1/2 multiplied with velocity va squared plus 1/4 r squared multiplied with va divided by r both squared. And again, this can still be simplified. So what we get is a real easy equation. On the left hand side we have the variables g and h, and on the right hand side we have only the variable va. So we can put it together, and what we get is g times h equals 3 divided by 4 multiplied with va squared. And well, g is a constant which we already know. It equals 9.81 meters per second squared. On the right hand side we have also given va, but we are actually not searching for height h, but for the angle alpha of the inclination. So of course we could take the equation and calculate h, but we don't need it, we don't want it, we want alpha. Can we get it? Well, yes, and we can get it relatively easy, because when we look back at our little sketch, we see that the height h actually correlates to the angle alpha when we know that the length of our plane is given as L, because the sine of alpha equals h divided by L. So we can substitute h, and what we get is that g times L times sine of alpha equals 3 divided by 4 times v alpha squared. And this actually is now really easy to solve, because we are looking for alpha, so let's put sine alpha on the left hand side, everything else on the right hand side. And the only thing that we are still needing is the inverse trigonometrical function. So we do not need sine, but the so-called arc sine function. And we can put all our given values into this equation, because they were all given in their basic units, and we can calculate the angle alpha as alpha equals 15 degrees. Well, are we done yet? No, if we look back at our given values and variables and what we are searching for, we realized that there was a second part that we are supposed to calculate. Namely, we are supposed to calculate now the velocity in relation to our initial given velocity if we do have a hollow cylinder of given inner radius. So how can we do this? Well, a hollow cylinder has a moment of inertia which is similar to a solid cylinder, but in case of a hollow cylinder, J equals m divided by 2 multiplied with the outer radius squared plus the inner radius squared. And what we know is that the inner radius is 80% of the outer radius. So we can take r equals 8 divided by 10 times the outer radius and put it into our equation. Then we have again only mass m and outer radius that have to be taken into account. Now, of course, similar to our solid cylinder, also in this case the hollow cylinder has to follow energy conservation. And we've already seen this equation. So this is not new. The only thing that is new is our equation for the moment of inertia, J. So let's put it right in here. And well, yes, it may look more complex, but we can make similar steps as before. Let's simplify it. Again, we can divide by the mass m all our three terms, And we can also simplify the right-hand side, and what we get is finally that g times h equals 91 divided by 100 multiplied with velocity b squared. What we were actually looking for was the velocity vb in relation to velocity va. So let's do it. Let's divide vb by va, and when you have a look, you can see that it can be simplified, and what we get really in the end, if we do it properly, is that vb divided by va is the square root out of 100 divided by 91 multiplied with 3 divided by 4. Finally, let's put it together, let's put it in a calculator, and what we get out of it is that the relation between the different velocities is 0.9. So, what is our conclusion? Yes, the hollow cylinder has a smaller velocity than the full cylinder. But this implies one additional thing. If the velocity of the hollow cylinder is smaller than that of the full cylinder, it means that the full cylinder will always arrive at the bottom faster than the hollow cylinder. Well, if you think about it, maybe in your mind it's weird, then yes, most people, if you ask them, would always say that no, the hollow cylinder will move faster. But that's just physics. And I hope this exercise helped you a bit to understand why this is the case. And if you're still not sure about it, go back and have a look at some of the formula, especially those of the energy conservation of the full cylinder with respect to the hollow cylinder, and you can actually see where the differences come from. And with this, I would like to thank you for your kind attention, and I hope it helped you. And if it did, give me a thumbs up. Please consider subscribing if you haven't done it yet. And I hope to see you soon for the next video. Bye!